Okay. So this is merge sort, different class. Okay, so we were working on the parsing of instructions under process. Actually, if I remember correctly, what we were doing at the end of class last time is talking about how do we create this scenario where a CPU can process multiple things after it's been interrupted. And that's where the whole Jabba the Hutt Princess Leia thing came in. So I don't remember who was Jabba. All right, so we have the process scheduler who talks to the CPU scheduler, and the CPU scheduler is in charge of making sure the CPU stays busy. So the CPU is Leia. It's a new Intel chipset. Core i7 Leia architecture, which has a very limited ability of just doing random I/O and moving crap. That's the limitation of its magic tricks. Okay, so a specific PCB is going to be running on the CPU until it context switches out. The CPU scheduler needs to be able to interrupt the CPU to send it a new person, a new PCB. Well, as we have it right now, we have a situation where when we tell our CPU to process, we built in this little variable last time I told you it's not going to work. So we have this, we need a fork. Yeah, so Jabba and Leia need to each be running in separate processes, so they're going to have to fork. But for our interpretation, we're going to actually do this as threads. So we're going to have our CPU scheduler running in its own thread, our process scheduler running in its own thread, our CPU. Does the CPU need to run on its own thread? Probably. So we'll have each of these entities. If we're translating this into kind of real life, if it's a piece of hardware, it definitely needs to be in its own thread, because this definitely exists as a standalone component in our computer, right? Inside the operating system, we have various pieces of the operating system, and if we can answer the question that a process scheduler might need to do something at the same time as the CPU scheduler, then it should also be running in its own thread. Make sense? Okay. So we need to go back and we need to thread this. Well, let me ask you this. Does a PCB need to be in its own thread?
No.
Why not?
Because it's pretty much just it's just a container holding the information for each.
It's a data structure. Yeah, it's an object for holding some information. It's not something that, it's something that is utilized to accomplish other things, but it's not something that does something on its own. All right. So, if you remember, a while ago we looked at an example of threads. We had a little worker bee thing here, where we decided any object, so we created an object called worker bee that extended something called a thread. And threads implement a interface called runnable, which forces us to have a public void run method. And anything that happens inside that method is what this thread does. Okay? So we're saying in this run method, we're just going to do this forever. That's what this particular guy did. So we're just going to print out this thread's name and the count over and over and over and over again. And if you just want to see that again real quick, we can comment these two guys out. We can create a worker B, WB1 is equal to a new worker B, and this constructor took a name maybe? Yep, name. Java 2Bs?
Yeah.
And then worker B, WB2 is equal to new worker B, Leia. That's not right.
No.
That?
Yep.
And then we'll tell each of those guys to start. Now, we'll notice that our worker bee does not have a start method in it. The start method is what we inherited from the thread class, which knows how to magically do the simulation of forking to create threads instead of processes. So we'll tell each of those guys to start, which then does the magic, which then calls the run method. So we should have two concurrently-ish running threads that should be fighting for I/O time. So Jabba, Leia, see it kind of flipping back and forth. So we can almost view that as us seeing into the window of CPU time. Ish. Even though a thread is sharing the CPU time within the single process. But that's how threads work. So what we're going to do is we're going to make our process scheduler be a thread. And we're going to go ahead and create our public void run method here. We won't have it do anything yet, but we'll just put it in there so we're ready to have it do some stuff soon. So we just converted our process schedule into something that is a thread. We need to do the same thing with our CPU. We're going to say our CPU extends thread. And we'll go ahead and have the run method for that guy. All right, now currently we do not have a CPU scheduler object. So we're going to go ahead and create that because as we see in our little diagram here, we have a CPU scheduler represented. Right now we've just implemented process scheduler and CPU. So we need something that's going to be in charge of the CPU. So we're going to go ahead and create a new class. Call this guy CPU scheduler. And we can go ahead and right off the bat say this guy extends thread. And then we'll put our public void run in there. And we'll make our constructor for our CPU scheduler. Public CPU scheduler. I'll have it take in no parameters. And one thing the CPU is going to do is it's going to control the CPU, or CPU scheduler is going to do is it's going to control the CPU. So this guy's in charge of a CPU. So we're going to have a private CPU, the CPU. And inside here, we'll set this dot the CPU equal to a new CPU. So we'll create an instance of our CPU thing here. Ultimately, what we'll probably also do inside of our CPU schedulers, we'll tell the CPU to start. Spin up that thread associated with the CPU. So when the scheduler comes online, it instantiates our CPU. So in real hardware world, it would check in with the CPU and create that link, and then tell the CPU to start working. Make sense? Okay, we won't do that yet, but that's kind of the direction we're going. Because this guy is a thread now, our CPU, we need to tell it to start, but our CPU needs to know what to do when it starts. And right now, we've kind of, at a high level, decided, well, it's probably going to process when it starts. So we'll probably say this dot process potentially among other things inside of the CPU's run method, but we won't do that yet. Just kind of foreshadowing a bit. All right, so CPU scheduler is in charge of a CPU. We're going to say that's all it does right now. All right, so now we are connecting some of our dots here to actually simulate stuff. We'll do everything from driver right now. So we're going to have our process scheduler, psched. It's going to be a new process scheduler. Instantiate that in our driver. And what does that guy do? Actually, we didn't even write a constructor for process scheduler, so we are given the no argument constructor that does nothing because all of our queues are built for us. That's fine. Not a big deal. We actually probably... I'm going to go ahead and write... I'm going to write the constructor for this because we are going to probably fill it with some stuff. So we'll say public process scheduler. How about take no parameters? And we'll leave it empty for now. Chances are this guy's going to be in charge of starting himself. Down the road, what we might do is you might create a operating system object that creates all the different pieces of the operating system. No, actually, we should probably just do that now. Let's do that now. So I'm going to create another class. This guy's going to be our OS, operating system class. Okay, and the operating system is going to have several things that it is going to have that through the rest of the semester we're going to be evolving. But for right now, we only know about 2 of the components of the operating system. Process scheduler, CPU scheduler. So we're going to have a private process scheduler, psched. And we'll have a private CPU scheduler, csched. I'm not sure if I like those variable names, but we're going with them. Then we'll create our constructor for our operating system. And right off the bat now, so what you should be thinking here is as your computer is booting up and Windows or the Mac OS is launching, these various aspects of the operating system are being instantiated. So as the operating system comes into being, we're going to have to set this dot psched equal to a new process scheduler. This dot csched is equal to a new CPU scheduler. And then we'll more than likely tell each of those guys to start. We'll just do it for now. So this is instantiate the process scheduler and start its thread. The second guy down here is instantiate the CPU scheduler and start its thread. Now we need to figure out what those threads should do, what the run method for each of those guys does. Okay, and internally we know that the CPU scheduler, when it gets created, where's my CPU scheduler? Let's get rid of worker B, they'll all fit then. There we go. CPU scheduler creates an instance of our CPU. So we'll link the CPU scheduler to the CPU. In our simulation, this means create an instance of the CPU. Okay, but in real life, when the CPU scheduler starts up, it's going to go and find the physical piece of hardware that is the CPU and create a link there so we can talk to it. Okay? In this case, the CPU scheduler actually creates the CPU as well. And then more than likely, we'll also tell the CPU to start here. Start its own thread. Okay, and we may end up moving around some of those things about the starting of the threads and that kind of stuff, but for right now, we're going to say this is good enough. Okay, and we're going to leave our run methods alone for right now. Now we need to consider how all these things connect. All right, so what we're trying to simulate here, is a process being born by our process scheduler, simulate a bunch of processes being born, send those processes to the CPU scheduler so that the CPU scheduler can then have the processes get executed on the CPU. That's what we're trying to accomplish. All right, so right now our CPU knows how to process mostly. Doesn't really know the I/O portion of it yet. We're skipping that for right now. But it knows how to do the parsing of the crap. So it can change the value of registers. Okay? And this is what happens when a CPU processes. And right now we have this happening as long as this dot should process is true. So somebody's going to set should process equal to true in order for that to actually start. All right, that makes sense? So we think about the order of operation here. For the CPU scheduler, a new PCB comes into the CPU scheduler. The CPU scheduler then sets the CPU's PCB. But let's see. That's at the CPU level, that's fine. We could have made an argument to have the context switch stuff be in the process or the CPU scheduler, but it doesn't matter. We'll just say CPUs know how to do the context switch stuff. All right, so did we do it in here at process? We don't. Okay, good. So I'm going to have public void context switch. That's going to be the only method, only context switch method that we're going to keep as public. The other ones we're going to make private within our CPU class. Now, whenever something comes to the CPU, whenever a new PCB comes to the CPU, we know we need to context switch out, and then we need to context switch in. Those two things need to happen, correct? Now, to context switch out, actually I'm going to move this method up by the other context switch methods. You can leave yours wherever, but just so I don't have to scroll as far. When we context switch out, we're going to set the cur PCB's program counter to what it should be. We're going to set the PCB registers equal to what it should be. And then copy them over. And then set cur PCB equal to null. Now, when the CPU is told to context switch, we're only going to context switch out if we currently have a PCB. Correct? There's nothing to context switch out if the cur PCB is equal to null. That is, either it's the first time the CPU is running, or previously there was a context switch out, but nothing context switched in. Make sense? So, if this dot cur PCB is not equal to null, that is, if there's currently a process running in the CPU, we're going to go ahead and set well, we're going to go ahead and do this dot context switch out. And then we'll say this dot context switch in the PCB. Now this is going to happen every time regardless. So we can move that outside of this if statement. So when we generically tell a CPU to context switch, we're telling it, if you currently have a PCB, context switch it out. Then context switch the new one that I just handed you in. Make sense? Now, before we do that, we have to start considering that our CPU is currently running in a thread. Right, so I'm in the middle of doing these instructions. So let's go back to what we think process should be doing. This guy down here. So as long as this is set to true, which let's presume right now it currently is true. And I'm the CPU, right? I'm Leia, right? Yeah, good. Or were you Leia?
He was Leia because you fit Java on his profile.
Right. Okay. So Leia here is cooking. You just call me fat? All right. So, what's this?
I said those are pretty delicate way of
A delicate way of telling somebody they're fat is by saying they fit Jabba the Hutt's profile. I don't know if that's delicate. I had a student the other day tell me, I think it's even in a more delicate way, using your example, so significantly less delicate way. Show me this video, and I guess the video was of it was about fat people, and in the video it had this this cart thing that had two fat people on it, and they were being pushed by another fat person. And then they had the quote from the original Jurassic Park movie that says, "They do move in herds." So yeah, that was almost offensive. Not quite. All right. So got Princess Leia back here. You're doing your job, and your job is to process instructions. Okay, so we're going to assume this is just true, constantly true, constantly true. So you're going to read in the next instruction. You're going to increment the program counter. You're going to parse the instruction, do whatever it is you're supposed to do. Leia, pay attention.
Sorry.
Okay. Slave master. Okay. Princess Leia. All right. All right. So you're doing what you're supposed to do, getting the instruction, parsing the instruction, blah, 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 spinning back up, doing that again. Now, if we don't stop this process, if we don't interrupt this process, what then happens? If we just randomly tell our CPU to context switch, keep in mind, since our CPU is running in its own thread, this thing's cooking, right? And if I'm the process scheduler, or the CPU scheduler in this case, if I'm the CPU scheduler and I'm running in my own thread, now I can go and actually tell Leia to context switch when you're in the middle of doing stuff. And right now, the way our context switch set works is it just says, oh, if you currently have a PCB you're working on, go ahead and switch it out. And what does switching it out say do? It says save the program counter, save the current state of the registers, copy them over, and then set the PCB to null. At no point in time did I tell you to stop processing the current PCB. So we might have race conditions. In the amount of time I was context switching out, you may have moved on to another instruction, in effect changing the program counter. You may have new values in the register, so I may have copied the wrong values. And even if that didn't happen, let's say you hadn't quite gotten to the next step in there. So you were somewhere in the middle of processing an instruction. Somewhere right in the middle, I'm going to steal your PCB and turn it back and turn it to null. So the next time you try to access it, gone, nothing, null pointer exception. Blue screen of death. Make sense? Okay, so that's why the interrupt is important. I can't just start going and screwing with stuff on the CPU. I can't just start saying, oh, the program counter is going to be, it's static. This is what it's going to be. The registers are static. I'm sure you don't need the current PCB anymore. Okay, I can't just start doing that. I need to first interrupt you and say, finish what you're doing, then let me do this stuff. Does that make sense? Okay, so it's an important thing that needs to happen. So right now, our process method spins as long as this dot should process is true. So when the CPU scheduler requests that the CPU does a context switch, the very first thing we need to do, context switch, I switched the order for a reason, there we go. Very first thing we need to do, tell the CPU to stop working after the current instruction is processed. So we say this dot should process is equal to false. That make sense? This dot should process is equal to false. That's what should happen. Now, if you are currently in the middle, if Leia's currently in the middle of processing, so we're sitting here, we're chugging away, let's say we're somewhere here in the middle of the else here, and we switch this should process to false, that doesn't hurt anything. You're going to still finish what you were just doing. Then the next time you spin up, you're going to fail right here. Does that make sense? Now we need to have a way for you to now notify me, okay, I'm done with what I was doing, go ahead and do the context switch stuff. Make sense? So we're probably going to need another variable here. We're going to have a should process. It starts off as false. We'll have a can context switch. Starts off as true. So now in context switch, we're going to set should process to false. And then we're going to say while this dot can context switch. Here, I'm going to just be explicit. While that's equal to false, do nothing. So we're going to sit here and just spin. We're waiting. This is kind of prior to interprocess communication type techniques, but okay for what we're doing right now. Okay, so we're doing nothing while we wait for the CPU to finish processing the current instruction. Now, we know we get past this as soon as the CPU finishes. Only if the CPU sets context switch, can context switch to true. So in our process method, as soon as we break out of this while loop down here, we are done processing the current instruction. Let the system know that a context switch can happen. So that's setting can context switch to true. You see how we have these moving parts? They're all kind of working together. So CPU's cooking. While the CPU's cooking, can context switch needs to be set to false. So that means when we first tell our processor to go, this point in time, no, it's not going to hurt anything. I was going to say we could put it inside the while loop here so it resets itself every single time through. That would be inefficient. We could say it here, but if something between this line and this line occurs, where should process is immediately false, we'll fall past it and just switch can context switch back to true. So switch the variable twice as opposed to switch the variable every single time we go through process. So this is probably, from a simulation perspective, reasonable. So when we tell the CPU to start working, the very first thing the CPU says, okay, I'm getting to work, don't context switch me without asking. So we say can context switch equal to false. Then CPU starts working. Okay? CPU's trucking until we come in and interrupt the CPU. How are we interrupting the CPU? We're interrupting it by calling context switch, setting should process to false. Then we start checking can context switch, waiting for the CPU to switch the context switch to true so that we know we can continue on. That make sense? So once we get past this, the CPU has finished the current processing and has notified us, but notified in quotes because we're not actually using notification stuff, that the CPU is ready for a context switch. All right. Now, our context switching algorithm is if there is currently a PCB, which means the CPU was actually just working on something. Otherwise, we would not have had to wait very long here, right? Can context switch would be true right off the bat. So if we're currently are working on something, then we're going to context switch that out, knowing now confidently that nothing's going to change in the registers of the program counter because our CPU is currently not doing anything. So we'll context switch that out. We'll context switch our new guy in. After we do that, what do? We tell our CPU to go again. Right? Now the CPU is the thread. Right now, our thread is stopped. And let's kind of show you why. Right up top here, I put in run. I'm going to say this dot process is what we do in our run method. And this dot process is what we do in our run method. So run is going to complete once this dot process ends. When does this dot process end? It ends as soon as should process switches to false. So whenever we tell the CPU to start, I'm actually going to get rid of this method right here. That's what we were trying to do last time, that when we hit the block. That was kind of our externally trying to talk to this dude. So we're not going to do that now. So we're just going to remove the set should process. When the CPU thread says start up, go, before we call this dot process, we're going to say this dot should process is equal to true. And then we'll call process. Okay? That's what it means to run. Similarly, we probably could have put that right at the beginning of process. We could have said this dot should process is equal to true right up here. We might even argue that this is better. We're saying we should process and we should not context switch. Right next to each other, this kind of reminds us that these guys are related. Okay? These guys should never be the same value. That would be bad. So let's do it at the beginning of process. We'll just set both those variables there at the beginning of process, which means we don't need this line here. It wouldn't hurt anything, but it's just redundant. So the run method for a CPU just says process. That's what CPUs do. They process. And we're going to process as long as we can, until we're asked to do a context switch. Context switch does the magic, sets the should process to false, hoping that this thread eventually ends. While we can context switch, we're going to wait. We're probably going to come back and, while we can't context switch is what that says, we're going to wait. We're probably going to come back and change the way this works. Okay, but for right now, we're going to say this is okay. Then we're going to context switch out, context switch back in. After we've done that, is the CPU ready to go again? It is. It's ready to go. So what do I do? So Leia, you're ready to process. How does the CPU process? Call run again. Okay, so how do I do that? How do I call run again? Okay, tell me why you're wrong. I'll even try to trick you. Okay, call start. This method is related to the fact that our CPU is a thread. So we need our run method to always be called by the start method of the thread class. So it does the correct magic. Okay? So after we've done our context switch, we're going to start the CPU. This dot start. That'll get our CPU trucking. Make sense? Okay. So that's how we handle our context switch. Now, if I'm the, let's go back to our diagram here. I'm the CPU scheduler. Now, the CPU scheduler itself, in this example, just told the CPU we need to context switch. Okay? Why would the CPU scheduler do that? We want to think about the sources of context switching. Go back to our diagram. This will work. So this is our process scheduler, our process scheduler over here that keeps track of all these queues. This is the guy in charge of all the PCBs. So he's going to have his ready queue. He's also going to have his I/O queue, that kind of stuff. All right, so the CPU, all it does is work. We've built the context switching mechanics into the CPU object. So it's kind of like inside of this circle right here, we have the mechanisms for context switching. So when this guy wants the CPU to context switch, we tell the CPU to context switch. If the CPU wants to context switch itself, the CPU can tell itself to context switch. What are the circumstances where those things happen? When would the process scheduler, the CPU scheduler, when would the CPU scheduler let the CPU know that it has to context switch? Go ahead.
When it's time's up.
When it's time's up. Okay, so the CPU scheduler's job is to keep the CPU busy, and the CPU stays busy as long as, well, a couple different things happen. One, the CPU runs out of time, whatever that means. We're going to give it so many cycles or something like that. We'll figure out what that means. Or two, if the CPU hits an I/O. The CPU hits I/O. That means it can't work anymore, correct? The current process you're working on is an I/O request. We're done. We're done with this particular PCB. Now, if I'm the CPU and I'm done with the current PCB, what do I have to do?
Request a new one.
I need a new PCB. Okay, so I'm going to send that PCB, CPU scheduler. So the CPU has a PCB, the cur PCB, and it's been interrupted by an I/O request. CPU scheduler figures that out somehow. We're going to have those two communicate. The CPU scheduler and the CPU are linked in some way. Okay, so those guys are going to communicate. CPU scheduler now needs to, if it's an I/O interrupt, needs to let the process scheduler know that I need a new PCB because the CPU is currently not busy because it's gone as far as it can with the current guy. Similarly, as a follow-up to that, the CPU scheduler will also ask the process scheduler to add that current PCB to the I/O queue. Make sense? So the CPU scheduler hands the process scheduler the PCB and says, go to I/O or go to the ready queue. So if a PCB finishes naturally, runs out of time, CPU scheduler notifies the process scheduler this needs to go back in the ready queue. Alternatively, if the thing has an I/O interrupt, CPU scheduler lets the process scheduler know, here's the guy that was just on the CPU, he needs to get in the I/O line. Make sense? Okay, so we need to make sure our throughput, the way all these things are works correctly. So let's go back to our process scheduler. So process scheduler is going to get called by somebody else every single time a new process needs to be started. Okay? And what he's doing right now is just adding it to our generic queues. Somebody else in our operating system is going to call this guy. We'll deal with that later. We want to keep this relatively small for our little simulation right now, that we'll start adding pieces to it. So we're going to double click on an icon. Somebody determines that that's what's going down, calls our process scheduler, and a new process is born. Fine. So this guy is going to get called each and every single time the user starts a program. Now, what should the process scheduler, again, which is a thread that should do something, what should the process scheduler do on a constant basis? What's his job? He reacts to users double-clicking on icons creating PCBs. But what's his job outside of that? Those are side tasks. Oh, you need a new PCB? No problem, I'll create one for you. But the rest of the time, when users aren't double-clicking on icons, what does the process scheduler do? Where's my picture? Why can't I find my interprocess or my Leia picture? There it is. What's this guy's job? Okay, keeps track of all the processes. What does that mean? Okay. Okay, well those are the queues he's managing. But this guy's a thread. We've decided to implement this guy as a thread. So he's going to be constantly doing something. Constantly doing something. Who's in charge of when the CPU, let's just say we never have I/O requests. Let's keep it simple. So it's always an example that a process or PCB gets the CPU for an amount of time. Then he's done. Who keeps track of that amount of time? This is the slave driver right here, right? Slave driver sends something into the CPU, takes that away. All right? So these two guys work in conjunction. What about the process scheduler? What's his job? What does he do on a constant basis? This guy on a constant basis monitors the CPU. We'll figure out what that means next time. He has to look at the current state of the CPU. What's this guy's job? He maintains these queues. He's got a list of all the jobs in the system. He has a list of he has the line currently waiting for the CPU. He is the line currently waiting for I/O, but in our example here, we're going to say I/O doesn't exist. So he's the line waiting for I/O. How does he interact? CPU scheduler comes and asks the process scheduler for the next PCB, right? And this guy will hand him a PCB, but does he do anything on his own outside of that? This guy kind of just makes himself available to the system. So this guy responds to requests from somewhere else in the operating system for new PCBs to get created. He also responds to requests from the CPU scheduler to get a new PCB. He also responds to requests from the CPU scheduler to place a PCB back into one of the lines. Okay, so this guy is constantly ready to respond. That's his job. Sit there and wait for one of the other operating system components to request one of your services. That makes sense? Okay, so he doesn't do anything on his own, which kind of makes sense. Really, out of all these, the only guy that does something on his own is our hardware, the CPU. Process. All right, questions about any of that? I said I was going to give you homework. Didn't I say that last time? All right, I'll give it to you next time. All right, I'll see everybody on Friday. We might have a quiz on Friday. That way when I come in, I say, well, we're supposed to have a quiz. You say, you lied to me once again. We will have a quiz on Friday dealing with something we just talked about today. So study today's class. Make sure you know what we're doing.